Hello guys and welcome back to my YouTube channel. So this is the first video in competitive programming with Python series. So today we'll solve this lead code problem, friend circles. So this problem is about a graph theory. So there are some n students present in a class, and we are given an n cross n matrix. So which represents the friendship between those n students. So each row in this n cross n matrix represents the friends that the student has. So here 1 represents there is a direct friendship between those two students, and 0 represents there is no direct friendship between those two students for ith row and the jth column. So ith student and the jth student has a direct friendship or not. So the main significance of the matrix is like that. So here the friendship, there is one more thing to notice. So the friendship is transitive in nature. So let's say we have 3 students A, B and C. Here A and B are directly friends and B and C are direct friends. So due to the transitivity property, A and C are also become friends. So keeping that in mind, the question tells us to find the total number of friend groups are present in the class. We need to count that and return that. So this is clearly a simple question of graph theory. So here we need to find the number of connected components that is present in a graph. So this n cross n matrix can be considered as a graph, and the students are considered as a node. So let's take an example. So here this circles represent student and the line represent the friendship. So let's say we have this 7 students, and here are the links between them. So here these 2 are friends, these 2 are friends, and these 2 are friends. Similarly, these 2 and these 2 are friends. So because of the transitivity property, we will have structure like this. So here we need to count that we have this friend circle and we have this friend circle. So we need to return 2 as an output. So this we can do this easily using the BFS or DFS. So in this video I will tell you about DFS. So DFS is nothing but depth first search. So in depth first search we explore a node by exploring its neighbor first. So we will go to the first neighbor and we'll explore its neighbor. So we'll go in deep and deep, and then until there is nothing to explore, then we will again trace back to the original node or the first node that we started exploring. So I will take a variable count equals to 0. So it will count the number of friend circles that we have, and then we'll have a set scene which represents the nodes or the friends that we have already visited or we have already explored, which I will take it as a set. So I will use the Python properties of set. So set is nothing but a collection of objects or collection of values. So inside the values are unique, so that's why I'm taking, and we can search for any value present in the set in order of 1 time. So it is efficient as well. So we will iterate through all the students, and we will one by one, and then we will check if it is not visited, then we will go do the depth first search for the students. If it is visited, then we will skip that part. So here number of students is nothing but the length of the matrix given. So or the number of rows in the matrix. So I will check if I is present in if I is not present in the scene, like I is not visited, then I will go I will do the depth first search. So first of all I will increase the count. So why we will increase the count? But let's say we are visiting the first student only. So the first student will be in the first friend circle. So I have to increase the value of count to 1, and then I will add that student to the scene list. So I will use the add property of the set, and then I will perform the DFS operation. So I will define the DFS operation later. So now I will what I will send is I want to do the depth first search on this this on this very student, and then we will complete this for loop, and at the end I will return the count that whatever the number of friend circles that has been found, we will return that. So now I have to define the now that I have defined the structure of the code, now I will define the DFS structure or the DFS function. So I will define the DFS function. So here I will get let's take it a good name. So let's take this as student. Okay, so now that we are in the DFS cycle, so I will explore the student's friends. Like I will go to each of his friends and perform DFS on each of their students or each of those friends. So I will traverse from for I in range length of met m. So length of m is nothing but the number of rows present in the friendship matrix. Now I will check if m of the student that I am considering and the friend that I am considering is equals to 1 or not. So I will just check for its truth value, and I will check that if that student, that the friend student is not is already visited or not. So if it is not visited, then we will visit it, else we will just skip that iteration. So yes, I have seen that if not in scene, so if I haven't seen that, then I will add that node or add that student to the scene list. So I will add I into it, and then we'll perform DFS on that very friend, that new friend, so that we have just encountered. So I will perform DFS on it. So it will recursively do DFS on each of the neighbors, and then at the end it will return. So what happens will that I will start with the first friend. I will reach out to his friends, then I will perform repeatedly. So I will get a connected component. Then after that connect component is completely iterated or completely explored, then I will return to the original list. So now that I have added some nodes in the scene set, so it will skip those iterations in the main program, and it will only iterate for those students who are not in the scene list. So and at the end we will get a count of number of connected components. So let's run this code. Yes, it is performing good on the test case. So let us change the test case. So yes, it is performing good well on the second test case as well. Let's submit this code. So yes, the code is accepted. It is performing around 46% better than the online Python 3 submissions. So it is good enough. Not the best, but not the worst as well. So that's it in this videos, guys. I will share this code in the description box, so it will directly point to the GitHub repository where I will have all my competitive programming codes available for everyone. So that's it in this video. Thank you for watching. Thank you for your time. This is Raj signing out.